Hey folks, Sebastian from Madrigal here. If you've been following me for a while, the scene you're looking at should be familiar to you. This is a level from a game I'm working on, codenamed Project Slide, running on my custom game engine called Basis. Here I'm just driving around leisurely without any enemies or objectives. I just want to see how the game looks and runs. Up in the top right corner you can see the frame rate, which is sitting at a comfortable 60 FPS, at least most of the time. You can see that the game is rendered using the Vulkan API. But what is WebGPU? I'll answer that question in a little bit, but before I do that, a little bit of background. A few months ago, I took it upon myself to make the Basis engine support the Vulkan API. Now, Vulkan, if you don't know, is a so-called modern API, which means that it is designed to give the application programmer direct control of the graphics hardware, or at least as direct as you'd like. It also means that Vulkan is significantly harder to program for compared to the old-style graphics APIs like OpenGL or D3D11. Now, Basis has used D3D11 as its home API, if you will, for many years, and I decided it was finally time to properly support Vulkan. So I ended up coding the whole Vulkan backend on video, and you can find the video series on my channel if you're interested. I'll also post a link in the description below. There should be some interesting things in there if you're looking to write some Vulkan code. Now for that backend I used a helper library called VEC, which is supposed to make moving to Vulkan a little easier. For example, VEC handles the resource transitions for you, which you have to do yourself otherwise. Now I thought VEC really hit the sweet spot in terms of being low level but still help you out with some of the really small details. Because Vulkan wants you to lay out every single step of the graphics pipeline on a level that frankly I have no use or even understanding of a lot of the time. And with VEC I figured I had finally found the right level of low-levelness for myself, if you will. Now the end result of that video series and Vulkan backend was okay-ish. I got the game running and looking mostly correct, but the performance really wasn't where it needed to be. Now some of that was probably because of Basis's renderer and how it got in the way of a modern graphics API. Basis's renderer is not the most optimized thing ever, but some of the slowness was definitely coming from VEC itself. I knew even before I started that VEC was effectively abandoned by its original developers, and I got the feeling that I was pretty much on my own if I wanted to continue down that path. You can probably get a decent Vulkan renderer created using VEC if you put your back into it, but I kinda lost interest after a while. Now to be fair, the reason I didn't feel like perfecting my Vulkan renderer wasn't entirely Vulkan's or VEC's fault. Instead, I had heard of a new graphics API on the horizon. Something that would fit right in the same sweet spot as VEC, but with the added benefit of being supported on even more platforms and having multiple large companies working on it. In other words, it probably wouldn't have the same fate as VEC. Now that something was WebGPU. So what is WebGPU? WebGPU is a new graphics API, primarily built for the web and browsers. But if you aren't interested in writing web or browser games or apps, don't leave. I promise this gets really cool. If the old WebGL API is the web version of OpenGL, then WebGPU is the web version of Vulkan. And WebGPU was designed to be easily usable from JavaScript, WebAssembly, and the like. But it was also designed from the start to be easily usable from native apps, not just from the browser. And the use of WebGPU in native apps is what we're going to be talking about today. So for the rest of the video, I'm going to mostly forget that it exists in the browsers, as I don't work in that space. Now, as a small disclaimer, the WebGPU isn't final yet. But as far as I know, it's nearing completion, and in fact it's enabled by default in recent versions of Chrome, and other browsers and platforms will follow soon. Anyway, let's turn our attention to the native side now. So to use WebGPU in, say, a Windows game, you include it in your project as a library. So why would we want to use something like this? Well, WebGPU sits on top of existing APIs, such as Vulkan or Metal or Direct3D 12. And there are, in my opinion, at least two reasons why one might want to use it instead of using the aforementioned APIs directly. The first one is that WebGPU has an easier API. Writing Vulkan in particular is really difficult, and the other two is perhaps a little easier, at least in my opinion. But writing effective Vulkan code can be really, really tricky. The other reason is that WebGPU is essentially more cross-platform than any of the aforementioned 3 APIs. And by cross-platform, I mean it works on Windows, Mac, and Linux. And Vulkan works, as far as I know, really well on Linux and Windows, but Mac support is unofficial. WebGPU support, on the other hand, is just a library, so it can work really well on any of the platforms that you can build the library for. One way to think about WebGPU is like this. If you're going to use Vulkan or any of the other low-level APIs, modern APIs in your app, you need to write a significant amount of code between your app and the API to handle things like memory and synchronization, that sort of stuff. And writing that stuff is hard. If you aren't willing to spend a lot of time on it, you might want to have someone experienced do that for you. And you could consider WebGPU to be such a layer. And as an extra bonus, it also supports D3D12, Metal, etc., all from a single unified API. So that's pretty cool. Currently, there are at least 2 implementations of WebGPU outside of the browsers. In fact, these, as far as I know, might be the ones that are used in the browsers, but they're the ones that you can use from a native app. The first one, and the one that I ended up using, is Dawn. It's made for Google, it's written in C++, and you can include it just as any old C++ library, essentially. The other is called WGPU Native, and as far as I know, it has some kind of affiliation with Mozilla, but I'm not 100% sure. I haven't actually used this myself. It's written in Rust, but as far as I know, it can be used from essentially any programming language that can communicate with C, because it has a C API. Both of them are open source and they're free to use, and both implementations have C APIs, so they can essentially be used from any language with a little bit of work. As I mentioned, I've only used Dawn, so keep in mind that I might not know what I'm talking about when it comes to the other options. And by the time you're watching this, maybe there are even more implementations of WebGPU available. And while we're at it, also as I mentioned earlier, keep in mind that WebGPU isn't finalized, and there's bound to be some API differences between the implementations. In fact, there are some API differences between Dawn and WGPU Native right now. So basically, if you write WebGPU code today, the day this video is recorded, there's a reasonable chance you might have to change some of it later. But it has reached a point of being pretty stable, in my experience. And also keep in mind that WebGPU is delivered as a library, so you get to choose when you update, and in what fashion. Just like with any other library, so that's really nice. Now, one important and perhaps even a little bit controversial thing about WebGPU is that it uses a new shader language called WGSL. The reason about why they chose to do this rather than use, say, SPIR-V of Vulkan fame are a little unclear. There may be some technical reasons for this, some legal. I'll be honest, I'm not super happy about it, but it's not that bad. They claim that it would be trivial to turn SPIR-V into WGSL and vice versa. In fact, Dawn, and maybe other implementations too, do support SPIR-V modules in addition to WGSL modules. But in my experience, this doesn't work all that well. Especially like me, if your source language is HLSL. But I'll get to that in a bit. Now, WGSL as a language is okay, I guess. It's a little Rust-like, or perhaps Zig-like. It used to have a lot of weird non-standard syntax, but the people working on it have responded to feedback pretty well, and it's mostly comfortable to work with now, if you know any other shading language. I don't want to rewrite all of my shaders in WGSL, so I use a compiler, or transpiler, called Naga, which is part of the WebGPU Rust toolchain, to turn my SPIR-V into WGSL offline. This way I can massage it a little bit before it goes into the game data if needed. So let's look at the transformation flow that my shaders have to go through to be usable from WebGPU. We start with HLSL, and we feed that to GLSlang validator. GLSlang validator turns it into SPIR-V, the IR or intermediate representation that Vulkan expects. And this is the exact SPIR-V that we fed to the Vulkan backend earlier. We take that SPIR-V and we feed it to Naga, which turns it into WGSL. This WGSL can then be fed to the WebGPU runtime, which, if you're using a Vulkan backend for your WebGPU runtime, probably turns it back into SPIR-V again. Now this seems a little silly, but it kind of makes sense that it would do that, because if you consider that the WGSL should work with any WebGPU backend, whether that is a Vulkan backend or a Metal backend or a direct 3D backend, it kind of makes sense that WebGPU would take that and turn it into whatever the backend expects for that particular graphics API. Now, since Dawn actually supports SPIR-V modules, and I already had perfectly working SPIR-V, I figured I would just pass the SPIR-V to WebGPU directly. But as I already mentioned, that didn't quite turn out all that well. Apparently, since I use HLSL, my shader matrices are row major, and it seems surprisingly tricky to change that. WGSL doesn't support row major matrices, only column major. And if you try to pass SPIR-V containing row major matrices to Dawn, it just gives you a hard error and stops. I did briefly look into poking at the SPIR-V decorations to change the majorness, but it turned out to be easier just to have Naga do all of that for me as part of the transformation from SPIR-V to WGSL. And as an added bonus, since I do it this way, I get to review the WGSL and make any changes necessary offline before it reaches the runtime. I also have the option to just handwrite a WGSL version of a shader from scratch if I want to, or if a HLSL or SPIR-V shader that I have turns out to be particularly tricky to convert. Alright, let's have a look at this in practice. So let's look at the possibly the simplest shader in Basis, the copy texture shader. This is just a utility shader that I use if I want to take an input texture called GTexture here. We have a sampler for sampling that texture. We have a vertex shader, which just expects a full screen quad, and a pixel shader, which just executes over each pixel in the texture and writes it out to another texture. So very simple stuff. We also have the basis shader file, the accompanying basis shader file, which is a JSON file, and it has a bunch of entry points. We have a WGSL section here, and we specify vertex and a fragment and where to find the entry points for that. So let's run this, convert this into the runtime format. And if we now go into the temp folder, we can see, okay, first of all, this is not strictly normal HLSL. I have some auto bind keywords here, for example, that these are basic specific or basis specific. If we look at the preprocessed one, we see the full HLSL source code, which is passed on to GLSlang validator. And the SPIR-V is kind of tricky to look at, but this is what the output of GLSlang validator looks like. You can see that it has the same entry point. For example, we have GTexture, we have GSampler, and so this is a disassembly of the SPIR-V code. Right. If we go to the temp folder again, we can now look at the output of Naga. This is the input. The output for the vertex looks something like this. And this is WGSL code. It's kind of tricky to read because it just uses these _e something as parameter names, but you can sort of see that, okay, it's doing sort of the similar sort of thing. If we put this on the right and we take the original one on the left, you have like float 2, 2, minus 2 here, and you have the same thing over there, for example. And it gets you a vertex shader, and then we take the the frag part, which is arguably perhaps simpler because it's just sampling a texture. But you can see here that we have G texture and we have G sampler, and it generates a fragment for you. So this is the way that we get the original, if you will, basis shaders usable from WebGPU. There are some hoops to jump through, but it's not that bad. There are some things that are missing, or at least I haven't figured out how to use them from WGSL currently, though. Custom clip planes, for example, seem to be missing. So let's take this one step further and look at the runtime representation of these shaders in RenderDoc. So I'll just quickly inject into the game process. We'll click yes, and I think we'll just take a capture here in the main menu. That should give you a pretty good idea of what we're looking at. So if we take anything really and debug the pixel, you can see that this is what the shaders end up looking at runtime. I'm not actually 100% sure what I am looking at here. I think this might be GLSL. At least it seems to suggest that the memory model is GLSL 450. But yes, the generator is Tint. Tint is the WGSL compiler that ships with and as part of Dawn. So Tint essentially picks apart the whole shader and reconstructs it in the format that the backend expects. In this case, Vulkan, which means that this is what you're going to actually debug if you're looking to debug your shaders currently. So this is kind of tricky. You need to sort of mentally map this code to whatever you gave WebGPU originally. But there are some WebGPU debuggers on the way, I hear, which I'm very much looking forward to. So at this point, I would like to mention a few resources on the internet that are worth looking into if you're interested in using WebGPU for your native app or game. First of all, there's this very nice blog post by this person, Andy. I'm not sure of their real name, but I'll post the link in the description below. I want to talk about WebGPU, and this has some really actually nice history of how we got to where we are, and this goes into some more detail about like how this whole thing fits into the browser world, etc. But also considers the native side of things. So I would definitely recommend actually reading through this if you're interested in WebGPU. The other resource is the so-called WebGPU C++ guide by Elie Michel, I think is how I'm supposed to pronounce your name. I'm sorry if I'm butchering it. This is actually a really, really good, almost like tutorial of how to get WebGPU integrated into your C++ application, providing you're using C++, of course. But here you can, for example, choose between WGPU native or Dawn, and it tells you how to get those downloaded, installed, and then it goes into some basic 3D rendering and even some compute shader stuff. So definitely a very, very good introduction. This is a work in progress. It's written up here, but there are some things in here that I've had to actually ask about because the API is not stable yet. So why would the documentation be? It's kind of inevitable that something is going to be a little out of date, but nothing super tricky. And there's a very nice Discord group as well, and very friendly people on it. So a really good resource if you're looking to actually use WebGPU for your C++ application. So, what is using the API like then? Well, I previously coded the entire Vulkan backend on video, like I said, so if you want to see what that looks like, then check out the link in the description. But basically I have a common API called GFX API, which the game and the core engine uses to communicate with the graphics card. And this API is the same regardless of what actual graphics API is used. And the calls to this API are then forwarded to the actual API, which does the actual work. So let's have a look at one such class. The buffer class is probably a pretty good candidate. So we have a buffer WebGPU, which inherits from GFX API buffer. And just as an example, I also have a buffer D3D for the D3D11 buffer. But the WebGPU buffer actually doesn't look all that different from the D3D11 one. I do like the WebGPU API. I'm using just a straight C API. I don't even bother with any C++ layers on top of it. So essentially what you have are just loose functions, usually taking some kind of descriptor, in this case WGPU buffer descriptor. Here we're creating an index buffer, and the API looks very similar to any other graphics API. It does have some weird things like chains of things. You can typically chain together certain data types to sort of provide extra information that you wouldn't otherwise be able to pass. These, I don't know, may or may not be because the API was originally sort of designed for JavaScript, but I'm not exactly sure about that. But overall, I like the API quite a lot. I think it looks vaguely similar to Metal, and I think Metal is probably the nicest of the modern APIs to use. So definitely no complaints there. Well, how did it go? How did actually porting the renderer to WebGPU go? Well, in the past, I've added a Metal backend and a Vulkan backend, and I was able to get both of them up and running in about a couple of weeks. And I expected to get a working version in roughly the same time frame. But in practice, it took a little longer. Like if you're writing a new renderer from scratch and you're using WebGPU, then you'll probably get something up and running in a few hours. If you're looking to do that, then by all means look at the guide, WebGPU C++ guide. This is an excellent resource. My current renderer architecture, which probably could be called somewhat old school at this point, is not a perfect fit for WebGPU. Because WebGPU is very much a modern API in the same sense that the APIs that it sort of sits on top of are. I should create more things up front than I currently am, create less things on the fly. And I've had some problems with shader stutters, for example, because my renderer architecture expects to just chew through those things, but a modern API really can't do all that much. And I've had to rewrite some things in my renderer, such as the buffer handling quite a bit, and the end result is that the renderer got better and faster overall, and that means that the D3D11 path got even faster. And I wasn't able to get, or at least so far haven't been able to get the WebGPU backend to be as fast as the D3D11 backend. But it's pretty fast, and it's significantly faster than my raw Vulkan backend, even with the VEC layer. So that's nice. My biggest hurdle turned out to be WGSL. I was thinking I could just simply give it the spur V I used for my Vulkan backend, And I was wrong. It didn't work. And I was kind of surprised to see that WebGPU doesn't just pipe the SPIR-V through to the Vulkan implementation, but rather it picks it apart and puts it back together. But it kind of makes sense when you think about it. Like I mentioned, it needs to work with all of the backends, so it can't just feed SPIR-V to Metal, for example. It wouldn't work. But the whole shader pipeline was definitely the thing with most sharp edges this time around. And if you're porting an existing renderer to WebGPU, be sure to leave some extra time for that, because there could be some surprises there. So what do I think about the current state of WebGPU? Well, it's definitely a little rough currently. The docs are lacking and sometimes out of date or just plain wrong. But initiatives such as the WebGPU C++ guide definitely help. And tools such as Naga are very impressive, and they're improving by the day essentially. But there are still going to be bugs. I have had to debug the Dawn runtime a few times, which can feel a little overwhelming at first. But the fact that you can actually step into the graphics API runtime is really quite amazing. Compare that to something like D3D11, where you can't really step into any of the functions and see what they're doing. Of course, you aren't really debugging at a lower level than before, since you will still run into your graphics API calls sooner or later. But many things can actually be solved by looking at how the WebGPU implementation works. Knowing a little bit about the backend that you're using, so for example Vulkan or Metal or D3D12, helps a lot actually. If you see some state in a tool like RenderDoc and you decide that that state is not what you expect it to be, it's really nice when you can do a find in files inside your WebGPU implementation and see how it wants you to set the value correctly. And for that, of course, you need to know which function sets that state in the graphics API. And yeah, debugging in RenderDoc is a bit tricky. What you're seeing is not really what you gave WebGPU, but you can still figure some things out by just looking through the code, stepping through it, and comparing against your original code. But there are already rumors about WebGPU debuggers, so I expect this to change in the future. Perhaps even RenderDoc will get WebGPU support at some point, who knows. Overall, I think it's a pretty good time to start using WebGPU if you aren't afraid to get your hands a little dirty. And the more people use it, the better it will become. Finally then, I figured I would give a list of things I like or dislike about WebGPU in its current state. And good things first. The C API is very nice to work with. Much nicer than Vulkan in my opinion. It feels a little like Metal, like a cross-platform Metal. And I think it's the right amount of explicit, somewhere between D3D11 and Vulkan. WebGPU gives you the freedom to choose when to update your API, because it's delivered like a library. Unlike some graphics APIs that are tied to your operating system, you get to choose when you update the version of the implementation. Of course, it's sitting perhaps on top of an API which is tied to the operating system. So there is that. Truly cross-platform. I put a question mark here since I haven't used WebGPU on anything other than Windows so far, but the idea of the API is to be virtually anywhere. As long as the platform can support some API on top of which WebGPU runs, then you should be fine. And I would assume that includes game console, graphics APIs, etc. Fast. I truly believe that you can write a really fast renderer using WebGPU. I haven't quite gotten there yet, but that's mostly because of how my own renderer is set up, and there's some refactoring there to be done. Then some of the bad things. My biggest bugbear is WGSL. There's no way around it. I don't like it. I don't need another shading language with slightly different semantics than what I am used to. I guess I can learn to live with it though, and conversion tools are getting better. I just wish they would have used SPIR-V similarly to how Vulkan uses it. And some baffling design choices in Dawn. Dawn has some weird software engineering choices, like errors being issued by a callback system, which means you don't get the full call stack of the error. Instead, you get the call stack of the callback system, things like this. You can work around this with an environment variable, but then it just breaks into the debugger instead and doesn't fire the error callback. Things like this. I hear some of these things are being reconsidered, so let's hope for the best. And then a category that can be considered, I guess, both good and bad simultaneously. So, simplicity. The WebGPU API is definitely more limiting than, for example, Vulkan. There's only one submit queue, which means you can't record commands on multiple threads simultaneously. The only supported shader types are vertex shaders, fragment shaders, and compute shaders. For example, I use tessellation shaders in the editor. I'm not doing anything super complicated, but some people might run into some problems with these limitations, and that might be a problem. And then the fact that WebGPU requires you to think in terms of the modern APIs. I think for most people this is probably a good thing. WebGPU doesn't try to be or emulate something that it's not. It's really just a layer sitting on top of the modern APIs. But for me, for example, I have to rethink some parts of the high-level renderer because it's sort of written to be used with D3D11 style systems. So it will probably end up being better in the as a result of this, but it's a little bit annoying, to be honest. Okay, I am officially out of video script, and and it would seem also officially out of a voice. Let's just run the game and witness some of these glorious shader compilation stutters that I mentioned. This whole WebGPU project has been very interesting and also at times very frustrating to build, but I think the end result is that the renderer and the engine overall is just much better. Take a look at the water here. You see some weird movement there. That's because of those missing clip planes. I have yet to figure out. But yes, huge improvements across the board in the renderer, mostly performance related, but also, shall we say, logic related, required essentially by the WebGPU backend. And here we have some stutters as well. They kind of go away pretty quickly, but as we're loading materials on the fly, something that the modern APIs don't really like, then you end up with stutters like that. But yes, I think this is a pretty good outcome for a few weeks of work. And I haven't even tried running the WebGPU backend with D3D, not D3D11, but D3D12 or Metal on the Mac or anything like that. And that should be really interesting to see how that performs. And if it really does work with the exact same shaders as the Vulkan backend. But yeah, this is now running at a mostly a locked 60 FPS on this same machine that we ran this scene at, like, what was it, 20-30 frames with the Vulkan backend. So pretty impressive. Impressive stuff from the WebGPU teams. With that, I, as always, thank you for your time, and I hope to put out some more game dev related videos soon, and not just tech related as this one. And I also haven't forgotten about the Q&A video which I promised earlier, but that means that if you have some questions about any of this, you still have time to write that in the comments below, and I'll be sure to bring that up in the Q&A video. Anyway, as I said, I thank you for your time. If you have any questions, write them below, and I'll see you in the next build. Bye.